This is problem 14.26. It's on page 939. In a scattering experiment, an alpha particle A is projected with a velocity. Let me write down the velocity. And I won't redraw the figure in the book. It's a three-dimensional drawing on a two-dimensional page. Let's just write, in fact, I think I used V naught instead of U naught because we commonly use V in this text for velocity. So the initial velocity, it's just the velocity of A, but the initial velocity, in fact, I may have used V naught A. Let's see. No, I just used V naught. I probably should have used V naught A or VA naught, either one. It's just the initial velocity of A is negative 600I plus 750J minus 800K meters per second. So that's an alpha particle. It's injected into or it's projected, I should say, into a stream of oxygen nuclei, and they're moving with a common velocity. So this is the initial velocity of both particles B and C, because what happens is particle A, the alpha particle, hits particle B, which is an oxygen molecule, and then bounces off that and hits particle C, both of which are minding their own business before the alpha, or not the alcohol, but the alpha particle came along and hit them. Anyway, both of those are moving at 600 J meters per second. So if you look at the figure in the book, the J direction is generally upward. So the oxygen stream is flowing upward, alpha particle comes in from the side, bounces around, and exits. Okay? After colliding successively with the nuclei, in fact, let me draw a little bit of it. So B is somewhere here, A comes along and impacts it, and then B goes flying off, something like that, while A, the alpha particle, goes over and hits particle C, which also is moving along, okay, such that C goes off something like this, and then A goes off finally something like that. Okay? Look at the figure in the book. It'll make a lot more sense than my drawing here. But generally, the Y direction is like this, X is off to the right, and Z is out of the page of this. So, of course, this is not all just in a plane. Obviously, A initially has components in the negative K direction, so A is actually going into the board at a significant speed. In fact, faster than it's moving in the negative X direction and in the positive J direction. So, again, you have to use your imagination. Basically, what they did is they gave us a couple of points along the path of B, a couple of points along the final path of A, and a couple of points along the path of C, called them C1, C2, A1, A2, B1, B2, so forth. So we can tell the directionality of these velocities. Okay, so I'm going to get rid of that. We don't really need it. You do need to look at the figure to do this. So I'm just indicating here, I didn't feel like writing both, B and C have an initial velocity upward of 600 meters per second. Okay. So after colliding successively with the nuclei B and C, particle A is observed to move along the path defined by the points A1, equals 280, 240, 120, where these are obviously X, Y, and Z components, and A2 is 360, 320, 160, same order, while B and C are observed to move along paths defined respectively by B1 is, let's see, 147, 220, 130. B2 is 114, 290, 120. I hope I don't copy any of these wrong. Let's double check. 147, 220, 130. Yes, that looks okay. C1 is 240, 232, and 90 in the Z direction. And then finally C2 is 240, 280, and then 75. So that's the collection of points. All paths are along straight lines and all coordinates are expressed in millimeters. So the coordinates are in millimeters, whereas the speeds are in meters per second. knowing that the mass of an oxygen nucleus is 4 times that of an alpha particle, so what does that mean? Well, that means the mass of B and the mass of C are 4 times the mass of A. Determine the speed of each of the 3 particles after the collisions. Okay. The first thing I think I will do is describe the velocities of A, B, and C after all the impacts based on these points. So if I were to write the velocity of A as a vector, I don't know what its magnitude is yet, but I'll just leave VA there as a magnitude. And basically what I'm going to do is use these 2 points to get a vector that points in the direction that A is moving, to get a unit vector in other words. How do you do that? Well, there's the final, there's the initial, right? It's at 360 at some time later, it was at 280. So you take the difference. You take 360 minus 280, and notice that difference, that delta, that change in position, is in the I direction, because that's along the x-axis. Okay? Do the same thing for the next 2 coordinates. 320 minus 320 minus 240. That's in the j direction. And then 160 less 120 in the k direction. Now this is not yet a unit vector, but it does point in the right direction. To make it a unit vector, I will have to divide by the magnitude of this. So what I'll have to do is take the difference between these 2. Well, the difference between 360 and 280 is just 80. I'll take 80 squared. The difference between 320 and 240 is again, well, 60 and 20 is 80. So 80 squared. And then the difference between 160 and 120 is just 40, so that's squared. So what I've done here is I've made a unit vector in the direction of the velocity of A. And so simplifying just a bit, VA equals 80, by the way, 80 squared plus 80 squared plus 40 squared, and then square root simply comes out to 120. So 120I plus 80 over 120J plus 40 over 120K. And we can simplify this just a little bit. This is 2/3 I plus 2/3 J plus 1/3 K. Well, let's not forget, sorry, I should be multiplying that. This is still the vector VA. And I'll tack it on here again. Just getting carried away with just the direction part. Okay? Same thing for VB. VB is whatever the magnitude is. I don't know the magnitude yet. That's what we're looking for. But to get the direction of it, well, I'll take final minus initial. 114 less 147. That's in the I direction. Plus, let's see, 290 minus 220. That's in the J direction. Plus, let's see, 120 minus 130. And that's in the K direction. You can divide by the magnitude. So root, any difference squared, well, the difference between those 2 is negative 33. Has to be squared. The difference between these 2 is just 70. That has to be squared. And the difference between these 2 is negative 10. And that needs to be squared. So that gives us VB. Once we simplify it all down as far as we can, turned out it was irrational. So obviously this difference is negative 33, this difference is 70, and this difference is negative 10. So we end up with something that is about negative 0.4229I plus 0.8970J plus, well, actually minus, because this is negative, 0.1282K. Same thing with C. That's whatever the magnitude is of C. Just want the direction then for C. 240 minus 240. Not surprising, it will be a 0. Let's fill in our denominator while we're at it. 0 squared plus what? Well, 280 minus 232. That with 30 difference would be 50, so it must be 48. And that's in the J direction, let's not forget. And then finally, last coordinate, I forgot a parenthesis, didn't I? So 75 minus 90. In the K direction, and that's negative 15 squared. And so this is roughly VC times, and of course the first term goes away, so we just have 0.9545J minus 0.2983K. And that's it. Now we don't need all the intermediate work. What we really need are these velocity vectors in terms of direction. So, in other words, these intermediate things are not particularly useful to us anymore. Right? I don't know that it will save me a lot of board space. There we go. All right. So we have our velocity vectors, at least the direction of the velocity vectors. Now, let's see. All of the collisions happen between the three particles. In other words, all the forces, the impulses that happen are between the particles. They're all internal. So what that means is if I take the sum of the momenta initially, now what I mean by this is the initial for both A, B, and C, obviously the mass of each, I guess we could say I naught, if you like. So I equals 1 to 3, or really it's A to C, right? However you want to say it. It will be equal to whatever the final momentum sum comes out to be, because momentum is not destroyed. There's no external forces acting. And so the momentum of the system remains constant. Okay? So what does that mean? Well, let's examine the left-hand side first. I'm afraid I'm going to run out of space here, but we'll try to tie it in as we go. So on the left-hand side, we have the mass of A times the velocity of A. So negative 600I plus 750J minus 800K. Let's think about the units, make sure they're all consistent. All of the masses will be in units of mass. I don't know what the mass is of an alpha particle or an oxygen particle. It doesn't matter. We could look that up if we want to. Why bother? Rather than using the mass of A, notice I haven't even scratched the surface yet for this, right? But for this, for A at least, instead of using the mass of A, I could simply use the mass of, say, B over 4. Because it's just a quarter of the mass of B, or the mass of C over 4. It doesn't really matter. But notice that not only does A initially have momentum, so do B and C. And so we have to include the mass of B times 600J meters per second. Again, units are all consistent, so I won't bother with those. Also, we have momentum from C, 600J. Now, I'm running into my other work here, but this is all the left-hand side. Now, this must be equal to it. Now, I think I can reuse this. I need the mass of A times the velocity of A. If I've got the velocity of A right here, let's move things around just a bit. Velocity of A, magnitude right there. And then we'll say this equals. Now, we're not done. What we've done so far is we've taken care of the left-hand side. It's all of this. And we've taken care of the first term on the right-hand side if I would just add mass of A. Yeah, there we go. Again, I don't want to use the mass of A. I would prefer to use, say, the mass of B over 4. Okay. Now, let's work with the next term. We've got it right here, basically. So let me cheat just a bit and say plus. Now, notice this all goes on the right-hand side. All of this goes together. The mass of B times this velocity. Do the same thing. Take mass of C, add that in, Now this is all the right-hand side of my equation. And now I don't need these points anymore, so let's get rid of those. In fact, I didn't need them, haven't needed them for a little while. Okay, so what do we see? 3 equations, 3 unknowns, because look, we can pick off all the I terms, and well, this one doesn't have an I term, and set them equal. In other words, in the x direction, what do we have? Let me do something. On the left-hand side of the equation, I could take this 4 and divide through. Let's see. Let me write it out a little more cleanly, then I'll erase this, because this is a bit of a mess. So if I divide through by 4, I'd have mass of B times negative 150I, just divided by 4, divide by 4 again, plus 187.5J, divide by 4 again, minus 200K. All right, so that's this first term, plus mass of B. Well, wait a second. If the mass of B appears everywhere, and the mass of B is the same as the mass of C, can't we just cancel the mass of B everywhere? So I don't even need to write the mass of B. That means it's gone here. I just need 600J plus, well, cancel there too, 600J. And that's the whole left-hand side of my equation. And that is equal to the right-hand side. Now I could put this quarter in here as well and just have VA times 2 over 3 over 4, well 3 over 4, well 4, 3, multiply by each other is 12, so 2 over 12, or 1 over 6 if you like, take your pick, I don't care. I'm going to write it so hopefully it's clear. 2 over 12I, and then 2 over 12J, plus 1 over 12K. So that represents this term. The next term, I'm going to need some space for, so let me start to erase this bit. So we'll have plus VB. Here I don't need to multiply by anything, so negative 0.4229I plus 0.8970J minus 0.1282K. Try to keep everything straight here. Taking care of that. I've got one more term to add on the right-hand side. So we're done with all of this. It's just this last term here. And I hate to do it, but I think I'm going to break the line and say plus VC times 0.9545J minus 0.2983K. All right, things are a little bit cleaner now. So we've got all of this equals all of this other stuff. Now let's put this together. What would we have? Well, let's just go ahead and pick off the equations. In the x direction, picking off all the I terms, what do I have? On the left-hand side, I only have negative 150. And on the right-hand side, well, there's an I term. It's VA over 6. That gives me one I term. Here's another I term, minus VB multiplied by 0.4229. And that's it. There are no other I terms. So that's the x direction equation that comes out of the vector. The y direction equation, let's see on the left-hand side, notice we've got 1200 here plus 187.5. So that's 1387.5 on the left-hand side, because notice I'm taking this term, this term, and this term. And that has to be equal to, on the right-hand term, what j terms do we have? Well, VA 2/12, or in other words, VA over 6. My contribution from VA, from VB, we've got VB, or plus VB, multiplied by, let's see, 0.8970. It's this piece. And then finally, plus VC times 0.9545. That's this piece. Last equation we can extract is the z equation. On the left-hand side, we'll have, let's see, just negative 200. And that equals on the right-hand side, where's all my k terms? Well, a 1/12 of VA. And the next term comes from VB. It's negative, I guess I'll put the factor out front, 0.1282 VB, that term. And then finally for VC, minus 0.2983 VC. So there are the three equations that I need to solve. I don't really need the vector equation anymore because I've extracted all three of the component equations. In fact, I don't need the input information yet anymore either. Let's get rid of that. So if I could just solve these three equations and three unknowns of VA, VB, and VC, we'd have it. So looking at the last equation, if we were to take it and multiply it by 0.9545 over 0.2983, what would happen? Why would I do that? Well, notice for this term, the 0.2983 would cancel, and I'd have negative 0.9545 times VC, which will cancel this one perfectly. So then, if I multiply this through and add these two equations together, so in other words, take the y equation, add to it the z equation, what will happen? Well, let's see, we've got to be careful because we have to multiply this through on the left-hand side as well. So we'll have 1387.5 minus 200 times this factor, okay? Plug all that into your calculator, and what you will find, actually, pardon me, before we add those, let's do the multiplication, that way it's clear. So let's take this and do the multiplication. So let's just multiply 0.9545 over 0.2983 times negative 200. You get negative 640 equals because it turns out this ratio is almost exactly 3.2. 3.2 over 12 VA, I assume because of my round off, I assume it would have come out exactly to 3.2 just because someone designed the problem, so I didn't check too deeply, but it's close enough. I think I got 3.1997 or something like that. Close enough to 3.2. And it continued after that. Anyway, so minus the next term comes out to 0.41024 VB, not quite so friendly, but that's okay. I'm sure I had to round it off, or I think I did. And then, of course, the term we came for, 0.9545 VC, negative, of course. Okay? So now this is the new z equation. If I take y and add z together, or the new z, what will I find? Well, 1387.5 minus 640 gives us 747.5 equals, on the right-hand side, we've got to take 3.12 over 12 VA plus 1/6 or 2/12 VA. That's 5.2/12 VA. And then all we have to do is add the VB terms because we've designed the factor here so that these two terms will cancel one another. We get rid of VC out of the equation. So when we add these two together, we get plus 0.48676 or so VB. Okay. Well, that was nice. Pretty much combine y and z into this equation. Is there a way I could use this VB to cancel that VB? Yes. Let's just take this entire equation, multiply it by 0.4229 over 0.48676, you see. Because if I do that, then this term will cancel that one exactly. Now, of course, if these were both positive, I would have used the negative factor. But this will work just fine for what we're doing. Looks like we're still on the screen, so we're doing okay. So, what happens then when we multiply this out? We get 649.43 approximately. I went to decimals now instead of these fractions. 0.3765 VA and 0.4229 VB as planned, obviously. And I said, okay, let's take X and add to it this Y plus Z equation. This is the Y plus Z equation. That's where it came from. I want to add X to it because what will happen is these two terms will cancel, and I'll get rid of all the VB dependence. I'll have only VA. Then I'll have one equation and one unknown. So when you add these two together, what you get, let me move this back a bit, X plus the combination of the combined Y and Z equation, gives us 499.43, that's this term, minus 150, equals, notice these two terms cancel nicely as we planned, and then just adding these two together, 1/6 plus 0.3765, is 0.54316. I think the 6 are repeated. Again, I've rounded a bunch of stuff off, so I'm not completely certain, but close enough. So if we solve for VA from this, what do we get? You get about 919.5 meters per second. So there's the velocity of the alpha particle after it has bounced off the oxygen particle B and oxygen particle C. Okay? Now that's nice because we can take this VA and plug it back into the X equation, or perhaps even the X plus or Y plus Z equation, and find VB. I chose to plug it into the X equation, and I got negative 150 equals 919.5 over 6 minus VB times 0.4229, just from there. And from that I solved for VB. I didn't even show my work. I just subtracted this from the other side and divided through by the result. Of course, then flip the sign on my calculator because the two negatives cancel. It's another way to look at it. Well, then you need a negative sign there, but whatever. Anyway, I solved it. It was easy to do. It's 717.06 meters per second. And now that we have the velocity of A and the velocity of B, we can use, say, the Y equation if you like. It really doesn't matter at this point, to solve for the velocity of C. So that's, well, let's see. Let's just write it down. 1387.5 equals VA, but VA is 919.5 over, let's see, 6 for this equation, plus VB, but VB is 717.06 times 0.8970, that's this term. And we don't need any of this anymore, except for our answer perhaps. Plus VC times 0.9545. Easy to solve for VC. When you do, you find that VC is approximately 619.22 meters per second. Okay. And so there are the velocities of the three particles. It's interesting to look at the initial velocity of particle A, the alpha particle, and calculate its magnitude, because you've got the initial velocity as what, 600I, 750J, and 800K, well, negative. So compare the magnitude then of the initial velocity of particle A to what it has after all this interaction with the other two particles. And it could be enlightening, but I'll leave that to you.